Hello everybody. So in this section, or section 6.3.1, we're going to look at the auxiliary field H. But before we can introduce it, before we talk about it, we have to introduce it. So in the previous section, we looked at our vector KB, which is given by the charge on the surface, which is M cross N, and JB, which is the curl of M. Now we're going to ignore this part over here, and we're going to look at JB only. So before we saw that there is also another J, which is J free, or the J given by the current. Instead, and now we're going to have to put it together. So J total is going to be equal to JB plus J free. Now, how do these two differ? Well, JB is caused by the electrons rotating around the atom, so in the molecule. Well, J free is given by a current flowing through a wire. So if we put this together, we'll find what they both will give us. So for example, if we were to use a wire is actually made of atoms, molecules. The molecules will both have a magnetic field given by the electrons are rotating around the atom and the current. Of course, this wire connected to a battery. So now we can use something that we saw in previous chapters, and we remember that we have found the curl of B to be equals to J. Mu naught times J. So if we divide both sides by mu naught, we're gonna get mu naught on the left and just J on the right. So we know that J is actually equals to what? Well, we just proved here that is equals to JB plus J free. So JB plus J free. Okay? And then we can just say that JB, so J free is the same. JB is equals to the curl of M. This is from what we proved earlier in this formula right here. Okay, and so we can say that if we collect the curl, so we take this part over here on the left, we're gonna have cross product of B. So I'm just gonna put it over here. Because the product rules, we know we can put it there. Minus cross product with M is equals to J free, or if we collect the del cross, we're gonna have del cross with B over mu naught minus M is equals to J free. And we can say that this vector right here, because it's a subtraction vector, we're gonna call it H, and then we're gonna get that cross or the curl of H is equals to J free, or the curl of H, curl of H is equals to the magnetic field, the current density. We can exploit Ampere's law, because this is pretty much Ampere's law, and write it in integral form. So we know that the integral over a closed circuit of H is going to be equals to the current enclosed. The current free and closed, of course. We're going to write it free and closed. And this is very useful for what we're going to see in, for example, chapter 6.2, but it shows us that as long as we find H, we can find what is the current enclosed, or if we know the current enclosed, we can find what is H.